Hi, this is Sylvia and welcome back. I wanted to walk you through the exercise of building an OpenSees model using eSEES. And what I did was I found in the interwebs a reinforced concrete intermediate moment frame from a dissertation. I will show you this dissertation now. And I built the model using eSEES, which then generates and runs an OpenSees model. So I searched through the internet and found out this really interesting and very well written dissertation by now Dr. Michael Richards. It's a parametric study of ACI seismic design provisions through dynamic analysis of a reinforced concrete intermediate moment frame. So it's a nice frame because it's not a elastic or very stiff structure. It actually is a reasonable type of reinforcement. I went through and the dissertation is very well written. There's a lot of extra information about modeling and design and a lot of different highlights of philosophy and design philosophies that I think are of value even to just read for yourself. They built an OpenSees model using some tools that Kurt Hazelton had developed. So there's a lot of information given about the model itself, about the structure, and the results. So I'm kind of speculating and building my own interpretation of their data. So I don't expect to come up with a perfect response, or I'm just coming up with something different from what they have. But I thought it was a really good place to start since I don't have a real structure to show you. And here's just a completely independent type of frame. It's a very nice and straightforward example. It's a 4-story, 5-bay frame, pretty regular in its elevation, and there's enough input and information about the input. He's got information about the geometry and the concrete strength, the material properties that we need, the dead load and live load information, and boundary conditions. And then there's some good sketches about the cross sections of your beams and columns. And so this here inspired me, since there's this kind of information, to build a fiber section. So actually I have 2 models going, one using hinge models and one using a fiber section. I could expand it and use a fiber section with a concentrated hinge element and just really show many different cases. But I really just wanted to compare the 2 here just to show you the range of possibilities. So these are the cross sections, but then there's also information about the reinforcement details. It's great because the first 3 floors have the same reinforcement details. The top one has a different reinforcement details, and across the beam there's different information. It's not the same cross section across each one of these beams. So it's kind of makes it not so simple that it's the same cross section across. Very easy to model. So it does take time to build a model. But the drawings are really nice because they provide enough information. I even zoomed into this one here, and you'll see in the video that I'm going to have these slides on the side to kind of show where it is that I'm getting these different values. The video is going to be very little talking because there's just a lot of steps in between, but I'm going to give you the highlights as I go through the video. So it's interesting, you've got different type of reinforcement, and then even the column has one type of reinforcement for the first 3 floors and then a different reinforcement detail on the top. So this is what I have, and this is what I went with. They've got information even about the shear and the joint reinforcement. I am not modeling shear deformations nor joint deformations, so that's something to keep in mind. It's really cool because they've got these design documentation. So the first 2 pages are 1 and 2, where they provide you all the reinforcement details, but then they also provided a 3rd sheet, so I'm going to zoom into that, where they actually give the properties that they used for developing their OpenSees model. This is a figure from the report that tells you what these different properties come from. There's not quite enough information for me to know exactly what they were doing, but I think it's good enough for me to have a good first crack at it. What I did was I pulled out documentation from this backbone that they're referring to. These backbones have kind of changed with these materials, but I really try to do as good a job or as close a job as to what they were doing. So the columns have symmetric reinforcement, and so I can actually use a symmetric material property or symmetric behavior, while the beams have, positive and negative capacities. So I went through and I first computed all the properties for the columns and then all the properties for the beams. I did this using Excel just because there's just so many different cases. It's interesting because actually all the beams all have slightly different properties. So I selected certain beam properties. What's interesting though is it's got positive and negative reinforcement, but therefore there's a uniform beam section. It's the same section for the two ends of the beams. Or maybe that's just what they're showing here, and in actuality they did something different, and maybe that's why I have slightly different results. I'm not quite sure. I think I'm just going to have to go with what I have here. This is an example of a screenshot from eSEES. So as much as the process that I go through is I use eSEES to put in values and get an understanding of the behavior of the model. And then I used Excel. You can use Python. You could do this directly in Tickle, whatever program you want, to generate the many sections. So you'll see it. I do it in Excel in this video just to kind of show the graphics so I don't have to explain too much about what I'm doing there. Here's the results that they provided in their report. I'm really just going to compare the pushover curve with what they have here. I think they also give some fundamental period properties, so I compared those as well. And then they actually went beyond and looked at collapse capacities and probabilities, but that was beyond the scope of what I'm trying to demonstrate here. It'd be kind of exciting to be able to take this model and run these analyses now. They also did additional cases of a strong column, weak beam case, a 6-story frame. So I kept this documentation here just in case I have the time to go beyond this. So I hope you enjoyed the video. I'm not going to be talking too much. Please keep in mind that the speed of the video is 2 times the actual speed because I didn't want it to be a 4-hour. So if the video takes 1.5 hours, it means it actually takes 3 hours to build and run an OpenSees model, which is, I think it's pretty good. The point of eSEES is to take away the having to worry about the node definitions and this and that and the tedium of defining a model itself, so that then you can spend your time on deciding what are my model assumptions, what kind of cross-section behavior do I want to use, what kind of elements do I want to use, and that leads to a whole other discussion. But this is really to show you how easy it is to build the model. So I hope you enjoyed the video and you learned something from it. I definitely learned a lot by going through the actual process itself. Thanks. Enjoy. So you first start up eSEES and you save an input file. And make sure that you save often enough as you go through the processes. On the left, you'll see that I'm running through eSEES, and then on the right, I show the presentation where it is that I'm getting the properties. So first things first, you want to define your materials. We're going to define materials right now for a fiber section. So the first thing is a confined concrete, and then I'm going to define an unconfined concrete. And then I'm also going to define the reinforcing steel. You'll see in the process that first I choose steel 02 for my steel, but then afterwards I look at my section behavior and I don't like it, and so I switch over to a different material. This is very easy to do in eSEES, and that's the point of it, is that you look at the materials and you go, oh, I like this concrete. This looks like the concrete behavior that I'm looking for. You can even compare your unconfined to your confined concrete. So you do is you copy the materials, you test it as I'm showing here, and then you paste the results from the previous material. And so you can see here how there is a strength loss coming in from the unconfined concrete. So as I was telling you, first I try to decide, and it's really important, there's so many options as to what materials do you use. Well, my recommendation is you start with one, and then you see if the overall behavior of your cross-section looks like what you're trying to replicate. Remember, you're always trying to model something, whether it's a material or it's behavior. There's something that you're trying to match in a way or as well as you can. I'm showing you here how you can in real time, as you save your file, you can then look at your input file and you can see the different parts of it. You'll see as we go through this video that we're going to grow that input file. What I then next do is you want to define your fiber sections, and that's what's really nice about this layout that I have for this presentation. We're going to do the beams and the columns. What I did was for the columns and the beams, I defined the fiber sections to, well, the columns themselves to actually be symmetric in the two directions so that they're ready for loading, when we go to a 3D model. But here's to show you that, look, different cross sections along the beams, and these are the different beam types that I'm going to be developing. And so what you do is you start off with one. Here I am putting in the actual properties. So as much as I know and I'm given, I choose the different materials for the cover and the core as well as the reinforcement. Hey, I don't have any bars. Well, the interface allows you to put in your longitudinal bars. My picture doesn't quite look right compared to their sketch there, and so you could see that I did a better job in guessing what the cover is. I do have an amount for the bottom, but I wasn't given a cover top, and so I'm estimating values just based on the images. What's really nice and easy is you see you can just go up and down and increase the number of bars. There's many layers of bars, so make sure that you pick the right ones. And you see this, I don't like that at all. That's the problem with putting, steel O2. And so what I do is, hey, I'm going to change my reinforcement to be a different material. So right now I started with 60 KSI. Later I found out that it's actually 67. So you'll see that I updated that value later. But what's nice is that you can update it in real time. So you can loop through and go, wait a minute, I need more ductility in my steel. Remember, in real life, you would have an actual steel property or, something that's reasonable as to where you think the reinforcement should look like in the behavior. And then here's an example of what I was doing and just kind of playing around with it to see what kind of curve am I happy with. And so this is the curve that I chose for my hysteretic material. What's nice is hysteretic versus steel O2 is that, yes, you can do a multilinear curve. So it's not that much better, but there's a little bit more continuity in the curve here. And so I'm happy with it. I can save it as a beam. And so this is my exterior beam on a floor. So what's cool is that you save it. And then if you have other sections that are similar, you just edit it. So for example, here, I reduce the number of bars. It looks good. I save it under a different name. And so you go through this with all your cross sections. So I scroll down to here. Let's see what type of beam sections am I playing with. And you see it that I can do this for many different beam sections. Once I'm done with my sections, I look through here and I can show you all the different materials and properties that are, saved the input for those sections that I've developed. And you see it's a nice list of them. Now what I want to do is I want to do the same thing with the columns. As I was telling you, I'm going to make reinforcement going all around the column. I like to start over a section when I have a different geometry just to kind of clear out any sort of things that were saved. You can see here that So for this case, it's easy because it's a symmetric section. But in the next case, you're going to see that I had to play around. See, my cover was a little bit thinner than when I see in those columns, so that's why I saved it. So now you're going to see that for my intermediate columns on the sides, they're not going to quite look right, but you see how I have a second layer of reinforcement? And so the program takes into account that second layer of reinforcement when it distributes the lateral. So what I need to do is set the spacing for that second layer to be 0. And so now there's no second layer, and now you've got a nice, reinforcement all the way around the perimeter of your column. So I think I'm done with my columns. I'm just going to look through the drawings and see that there's just 2 types of columns, 6 and 12 bars. So I'm happy with it. I save it, and I'm going to just save the file itself. And here you are. You can see the input there. I will also go back and forth. If I need to edit, I don't like to use that little editor because I'm not quite sure it works. But I just use my own editor, edit the file, and upload it. So once you're ready, now we can define this elevation. So you can define the story heights. You have to set up the first story height if you want the next ones to be the same and not the default values. So you can even define it in inches, which is what we had, or as you can see, I have 30 times feet. In Tickle, you have to put the pound $ in front of it to be a variable, but feet are a unit. So it just kind of makes it look a little bit cleaner. Just be careful when you use units though, okay? But here I'm showing you that you can do it and it looks really cool. So there's our elevation, but right now this is just the geometry of it. I need to go in and assign the columns. So you select the beam and column input, and I pick what section I want at node I, what nodes J, and in the middle. This same as node I, and for the options at the very beginning, they kind of disappear afterwards once you've done one, so be really careful as you go forward. So you do want to define, even if it's the same section across, then you tell it, hey, it's the same section across. If you use the shift key, you can select more than one element, and here I'm showing you that, hey, it's the same column for all floors, so I'm going to pick the columns for all cases there. Be careful, I could have turned off the ghost beams and then selected everything, or ghost columns, but just showing you here as an example. So I pick a different cross section for this beam here, and then I pick that beam there and gone. So now we got to do the columns. I think we're happy with the beams. The columns, we know it's the first 3 floors have the same column, so we're going to pick node I and node J, and in the middle I'm using my cracked, actually for the fiber section I use the same cross section across for all of these. And remember, I make mistakes here, but just to not be exactly the same as what I'm supposed to do. But I was just trying to get through the exercise. There it is. I defined my elevation. And I wanted you to see how really cool it is in Tickle how the elevation is defined. Right there, there's the geometry, the way you defined it, and then all the different properties for each column length. You can actually define column line ranges and floor ranges and things, but the program itself saves them one at a time, one line at a time. So it's kind of nice because then you can go in and edit them. The next step is we got to figure out gravity loads. And so first you want to define load cases. So we're defining that we're going to have something called lateral live load and one that's going to be dead load. And then we're going to assign those values to our frame. First thing we have to do is compute them though. So we're going to then also define a load combination that's going to be live load plus dead load. Okay? So this is just a little formality so that then when you go to your model, you have the option to assign your loads to each one of these loads. And so here's what the input file looks like. It shows that the loads and load combinations. Now what you want to do is go in and compute what are these live load and dead load. So I'm using MathCAD here just because it's nice to dealing with units. And I'm going to walk through and kind of compute what the equivalent dead load and live load. Maybe I should have included the weight. I include the weight of the beams and of the slab, but I don't include the weight of the column. Maybe, I'm not sure if that's what they did over there, but I should have, just to kind of help with the period. But I feel like that weight isn't so much compared to the other elements and the live loads. So I didn't do it here. You could define the weights in different units themselves, but I find that right now with what I'm doing, I'm just going to use the basic units. So I need to define everything in kips and inches because those are the fundamental units that I chose at the very beginning. What I'm going to do is I'm going to define these dead load and live loads as distributed loads along the element. And so I don't have to put in the length of the element. I don't have to compute the total load, but I do want to compute a tributary width. I could assign a tributary width to this frame, but when you've got a condition like here where the width on one side is different from the other and the loads are different, it was just easier to define, integrate it across the width, and then assign a tributary width of 1 to my frame. So right now, this is just the easiest way to get around that. And so this is why you see that I'm multiplying it, because I've got different weights for the rooms and the corridor. So I define those two values, and then here I'm just adding them up. And that's going to be the input that I'm going to put into eSEES. And so I've got a distributed load of 0.133 for the live load and 0.19 for the dead load. So now I'm ready to go to eSEES and do it there, which is kind of cool and easy to do. So you go in and you go back to your elevation. Now what you want to do is you go to gravity loads. And remember, gravity loads are going to be downwards, okay? Downward is quote unquote positive direction. So I will go in and put a negative into OpenSees. So now I've defined the dead load, and remember to assign that tributary of 1. And then I'm going to, because it's the same for all the floors, and I think that could be different and that wasn't documented in the report. So you assign that lead load to all of them. There it is. And you pick, you could click on each one of those little arrow sets, or you just make it go in and do all that. You can actually edit those values once they're in, but this is just to show you how easy it is. I'm going to turn on how many modes I want to see, and now my model is ready to go. Let's see what I'm going to do now. I'm going to save it, and you can actually now visualize what the input file looks like. Let's visualize it. You scroll down to the model itself, and you'll see that on every beam, there is going to be a distributed load. There it is. And so for the each one of the 2 load cases. So that's in my eSEES input file, and I think I'm ready to check my eigenvalues and my fundamental periods. So let's do that. I'm scrolling down to find out what it looks like on their input. I don't think I wrote it down. So you need to select a model. You had to define what gravity loads you need to use for the mass. And here's just through OpenSees, it shows you those are my fundamental periods, which are pretty close. I think they have a period of like 1 point something. Yeah, so I'm in a completely different period from them. But for me, it's good to see, okay, I've got 3 fundamental periods that are relatively close to the ones over there. So I'm pretty happy with this model. And it's actually kind of cool because I have a fiber section comparing it to hinge model. So very different. Now I'm going to define a pushover curve loading. So I've got the same gravity loads, but now I'm going to displace it to a certain maximum displacement. I'm going to guess 10 inches. It's always a good place to start. And you go in, you select, what am I doing? oh, I need to update my reinforcement. This is when I realized that it was 67 KSI. So I can go in and just update my steel to 67 KSI because I saw that here. No big deal. Now I'm ready to run gravity. Let's just run gravity. Gravity is always a good way to test your model. And great, it didn't give me any errors. Now I'm going to look at, oh, and don't forget, you've got the little window that tells you what your periods are and that the analysis ran fine. It took me a little bit. Initially, I'm not showing you that I had put in gravity in the wrong units. So here's my pushover. I selected it, and it's running. I turned it on to visualize it. If you don't visualize it, it will run a lot faster, but it's always kind of fun to watch the curve. It takes a little bit of time for the program to do some post-processing, and so now it's done because it's a relatively quick analysis and small model. Sometimes the post-processing can take a while. So now I've got to figure out what was that maximum displacement that they went to. I went to 10 inches, but they went to about 2% of the floor height, and it's 4 times 12 feet, so I should have actually gone to 11.52. This is just to show you that, yes, you can go in and modify your load combinations, and let's just go to that. And now I can go back and rerun the analysis. Oh, and don't forget to save your file. And this is just to show you what the input file looks like, that you can actually see that it's going to go to 11.2 inches. Excellent. Let's run it again. Because it was so fast, you pick your model, you pick your load combinations. You can pick many models and many load combinations. And I'm going to scale my deformations. You got to make sure you're scaling the right things. There's a few different options there. You can visualize it. And so now I've scaled my deformations a little bit more so you can actually see it deform. This is a good way to check that the analysis is running. I think when you're running OpenSees and you can get to this point, you're always very excited. So it's nice how with eSEES you can get to this point a lot faster. There's the analysis, it's done. A little bit of post-processing. There. So now I want to show you how I deal with the results. So I've got my curve, I copy the data. And this is just a pushover data, maximum, it's a displacement at the roof versus base shear. I go into Excel, I paste the values, I should paste them up here, and I make a little graph. So this is just a repeat of that graph that's there. So now I want to overlay it over something that I don't really have those numbers there. So what I like to do in Excel is I'll go in, zoom in, take a screenshot of this object, paste it into my Excel as a figure, and then what I'm going to do is I'm going to put my graph and just put it on top. I want to make sure I go to the same axes as they do, or enough that I can overlay it. And I realize, wait a minute, they're plotting drift ratio. So if I take that and I have to divide it by the building height, which is 4 times 12 feet times 12 inches per foot. And so now I'm going to change my horizontal axes there. And I guess I did the wrong units there. Okay, now it looks a lot more reasonable. So now you take this graph and make sure that it goes to the same maximum drift or close enough, something that I can overlay. And I'm going to change my line to red so I can see it. And now what you do is you remove the background, no fill in your, see now it's a see-through, but you've got to move it to the front. And now you can overlay it. And you got to be careful, and this changes with the data itself. So every time make sure that you're plotting the same, but you see I'm overlapping my grids. And so look at this. My fiber model is really good in the initial stiffness, but it doesn't quite reach the same strength and deformation behavior. But hey, that's pretty darn good because these are completely different models. And so just make sure that you overlay things the right way. And so that's it for the fiber model. So now things get a little bit more complicated because now I've got this ASC 41 type of input parameters. So I went through and tried to figure out what input went with what material type. I just did not have enough information on that. So I'm really trying to do my best to interpret it. I went to the manual for the IMK materials to really get an understanding. The main thing is, how do you deal with that initial stiffness? Because sometimes they only deal with plastic rotations. And then what models are they using for the intermediate? If they're doing a concentrated plasticity model, what are you using for the elastic component in your beam or column? And so I'm kind of going with the data there. What I do first is I go into into eSEES, and I put in values to understand what are these input. Right now it's not fully documented. Oftentimes they do go with the material that's there. You can actually click up there on that plus, the OpenSees manual, takes you to the manual itself. But for me, it's just, I like to just play with it and see, okay, let me put in some predictable values and see what's what for the input. What I'm going to do then is I'm going to save this once I understand, and I take things off of defaults, okay? Because otherwise it won't save the default values. And remember, right now I think I'm just doing the columns, so I'm dealing with symmetric behavior, and I'm going to vary this and that so I understand, oh, okay, that theta p is not the total, is actually that increment of rotation, just as expected based on the graphics from the manual. But you can't count that what I did in the implementation in eSEES is exactly like the manual, because sometimes I try to make things a little bit easier. There's a lot of extra parameters in this modify IMK models that I'm not talking and hitting in this, because I'm really just caring about the envelope right now anyways. So once I'm happy with it, I can look at the different input. There's some really neat parameters on deterioration. But I'm not going to play with that right now, even though there I am. I'm putting in, oh, that's the residual strength. Okay, and so that I needed to scroll down to it. I'm going to save it. Then I'm going to look at the input file, how that got converted. I'm going to take that and I'm going to copy it over into Excel. And now in Excel, I can really do a lot more with my properties. What I've done is I've generated, those are the given properties from there, and I've done my best to convert them into what I can for the input for eSEES. So that was what I practiced before, and now in this piece of video, you'll see just the computations that I do. I'm not sure they're right, but this is what I'm going through, and just really to give you a demonstration as to how you can create this for more than one element. So I'm going to keep quiet here and just let you watch what I'm doing, and I try to do the best that I can for the section properties. Now I'm going to define the equivalent elastic section in the middle of my beam. I get the properties from what they've given me actually, which is a cracked or maybe not cracked, but it also takes into account the slab. And keep in mind that when I did the fiber section, I did not put the slab into my stiffness properties. So that's definitely something that I should have accounted for. But interestingly, I get the same initial, my fiber section is a little bit stiffer, so I'm not quite sure, but I think it's also because I'm not accounting for cracked sections initially in a fiber section, because that takes care of it itself. Now I'm ready to assign the beams because I've defined the properties. I'm going to assign them to each place where they belong. Remember, you got to define something in node I, node J, and you can define a different property at in the middle node. What you'll see here is I've left the default element. I'm looking ahead. I need to change element type, and it's interesting because you'll see later that I come in and it's pretty straightforward how you could do it, and you change that in the script. So you don't have to go in manually and redefine everything. And that's the power of having both a script and a GUI. It's a little tedious, it may seem, but it actually goes pretty fast. You remember, I'm showing you 2 times the actual speed, but it's relatively fast anyways. So I'm happy with that. I'm going to save it, and I'm going to look at the input file itself to kind of show you what it looks like when they're there. Oh, and I got a message on the right about something I needed to fix maybe, but oh, because I was playing around a little bit. But here's the beams, and I've defined the columns and beams, and there you have it. Now what I'm going to do is I'm going to copy the gravity load from there, from the previous one, put it into this input file, and now I'm going to change. You see I can say floor range and bay range for the gravity loads for both the dead load and the live load. And so poof, I copy it, paste it. Now I reload the file and it's there. Now I'm ready to run an analysis. The error that's there on the right shouldn't be there. But maybe I did something wrong, and so it's nice to kind of get the feedback to it. Best way to do it is you go in, you look, and oh, poof, there they pop up the right values for the right load. So I'm ready to run the analyses. The messages that I had there were from an old case that I messed up. So now I'm going to look at the period, and I'm going to, oh, I wanted to increase the number of periods that are associated with this model, so it prints them out for me. Yeah. So let's go back. We go to Analyze. Oh, you can see here that all the loads have been distributed to all the elements. Now let's look at the period, or run a gravity analysis and just display the mode shapes for this. And so this is the fiber section, which looks good. Okay, I'm going to save these periods and just in a screenshot to see if I get something similar. I'm going to look at more modes, and I start seeing something weird. Look at those really long periods. And these look like they're axial. That's kind of cool, though, I have to admit. Really long periods in the axial deformations. And I realized that in my hinge, the default is just the cross-sectional area is the geometry that I've given it. So I need to go in and make it axially rigid. So these are all axial modes. But there it is. I start seeing something that makes sense in these other periods. So I need to go and stiffen there I am. I'm going to assign, see, the A cross-sectional area. And I'm going to just put in 1 times 10 to the 9th. So you have to do this for both your hinge models as well as the elastic model for the beams and columns. And there it is. Now these are all lateral modes. In the lower modes, I've got reasonable values. Higher modes is fine. I mean, I got to have some sort of axial stiffness, but their periods are really, really short. So it's perfect, and it's as I expected. I'm going to now just run the analysis again, look at the modes, and see if I get something closer. Interestingly, I'm right on their periods, but then you'll see the pushover that I'm not on the same level. And so this is where something is up in the inelastic models, but that's okay. I'm really happy with what I've managed to pull off with not knowing anything about the OpenSees model. And my implementation in eSEES of a concentrated plasticity model is different. I don't go in and define extra elements, so it's really efficient using the force-based element. Here's my pushover analysis. I'm going to go in and compare the values to what I had before. What I'm going to do is just play around a little bit with the data here to be able to plot it the same way. So I got to remember that I got to plot the strain or the ratio, and then I'm just going to duplicate that plot and then move it over here so I can plot all 3 graphs. Excel will put a background back on it, so you got to turn off the fill again. So it's a nice way to overlap it. So here's the results that I get for this case. I think they're excellent, that I get the same base shear. I think the stiffness properties, interestingly, I have the same period, but the pushover behavior is different. And I'm going to try to do a couple of things here to see if I can get closer to their model, but I don't know what they did. So I'm going to see what can I do to stiffen the system? Well, one way to stiffen it is to, maybe they didn't use the cracked section in the column, maybe they use the actual section. And what I'm finding out here is, for example, that I was using, I think this is where I found out, I'm looking at the OpenSees and looking at the property and the input, but what I noticed here, I think, is where I realized that, hey, I was using a distributed plasticity condition when I should have used a concentrated plasticity condition. But I'm looking at all the different numbers and seeing, hey, what's going on. So let's see if I can go in and correct. See, I was using the default beam column when I should have been using the beam column concentrated hinge. So you go in and you do a global replace. You got to make sure you don't do it everywhere. So it took me a couple of iterations to find out what the right piece of script was that I needed to replace. So, and then I made a typo, so I had to correct that. And I left this here to kind of just show you, you can do it manually or you can do a global replace, and then I forgot to change a couple of them, just to show you that this isn't trivial, but it just kind of requires patience and time in debugging. The point of it is, though, it's relatively easy to catch mistakes that you may make, even silly mistakes like these. So what I'm doing is I'm doing a global replace here, doing a little bit of editing. Did I do it right? And so then I go in and I put that into my input file, reload it. What do I get? I go in and run the analysis, and I find out, if I visualize it, yeah, look at the mode shapes, and they look really weird. Like, oh, what have I done? And I had made a typo. Kind of got to find your way around your files. Oh, there I am. I finally found my way around, and I realized that I spelled that incorrectly. And so I need to copy and paste it and spell it correctly, because I'm assigning something. And I would have caught this if I had looked at my little window that communicates problems. But I knew that oh, there it is. I see it. So now I can run my gravity load or under gravity to kind of see what my mode shapes are, my periods. Great. They're what I was expecting. They're back to being similar to what I had before. And if I run my pushover analysis, this is running again at twice the actual speed. It's always feels good when you see it going nonlinear. Yay! It has run. Let's look at the results. You see, it takes a little bit of time. Imagine twice as much time as this to process the data, because I put it in. There's a lot of post-processing visualization that you can do in eSEES that I still need to work through. But if I copy these data and put them back to where I had them, I'm still softer, but the same period. So, but I'm really happy with just having gotten the same base shear strengths. If I go in actually and I changed it to using the gross section just for the columns, and yeah, you got to make sure that you don't change it everywhere. So if I replace it just there and I rerun it, takes no time to rerun the analyses. What's nice is just making these changes easy to make these updates. I did something wrong because, oh, I realized, oh, I needed to update the stiffness. So looking at periods and mode shapes is really helpful in debugging your model. So I wanted to make sure that that's there as well. You run your pushover analysis. I'm trying to just have a look at things. Okay, yeah, it looks good. Yay, my periods look good. Run the gravity analysis. It's always a good test. And here's my pushover analysis. Go nonlinear. Yay! I think we're almost done. I could keep working on this to improve the results, but again, I'm really shooting, I don't know what my target is, and I'm really happy with similar to what they were doing is, and I really wanted to give you a demonstration on how to do this for a 2D. I'm going to later record another video to do it in 3D. There it is. That's pretty good. I don't like how my strength is going up though. So again, I don't know what apples and what oranges I'm comparing here. So I'm happy enough with what I've gotten. Now I'm going to do an earthquake analysis just to show you how easy it is. You go in, you pick a ground motion that you have, you can visualize it even. I integrate the acceleration history. This is just from the Pure Ground Motion database. Interestingly, it's a really old version of the file. I'm going to scale it up by 10 just to make sure. And I'm going to run both the fiber model and the hinge model to kind of show you actually how the results are actually different between them when you're dealing with more than just a pushover analysis, because the dynamics are different. I'm defining a load combination, and you can put factors. You know, this is 90% of the dead loads. And so here's my load combination for my earthquake. Look at the file. It's kind of fun to see it because remember, you want to look at the file because you could do this by hand in a script versus having to do it through a GUI. Let's run the analyses for both models, and it's kind of fun to watch them. I'm running them sequentially. There are ways to run them at the same time, but right now let's just run them sequentially. What I'm going to do now is I'm going to plot just the two different displacement response and show that the fiber section does not capture the offset while it does the hinge model does. But it really depends. It just happens to be the case today. You really have to evaluate many different models. And this is just to show that they do give different results. Hi, I'm back, and I wanted to walk you through the final input file that we have for the model itself, and also the OpenSees input files that we have for the pushover and for the ground motion analyses. Because a lot of times with a lot of cases, as much as a graphical user interface is great, I think it's that much more efficient and faster to then, if you've got a really large model, to work on a script. And maybe you could do something in Excel to even generate the scripts that generates the input. So there's a lot of different things you can do with it. So I wanted to show you the simplicity of the scripting component of eSEES, because I think this is really what makes it cool about it. What's great about using the graphical user interface is it gives you all the default values. It's got a lot of, additional options that it reminds you what kind of input you need to put in it. But at the same time, in the script, you can be very clean because you only have to define the key parameters. For example, there's always going to be, you're going to see some extra things that are defined that are just needed, but they kind of make sense. So for example, for confined concrete, all you have to define is F prime C. Then for reinforcement, you're using this model here, and these are the properties that you have. So remember, in OpenSees, you use materials to even just define behaviors, and so it's the same thing in eSEES. And so here are the properties of the exterior column for the 4th story, exterior column for the 3rd story. It's kind of nice because you can call it whatever you want, and then that's what you refer to it later. And it makes the input file, almost self-documenting. And these are the different values that are here. You can actually loop through these and define arrays and do a cleaner job than just specifying these one after the other. But, here's the material properties for the columns. Then we've got them for the beams. Here's your exterior beam 1, exterior beam 2. So you can see the properties are almost the same. So you can, if you have a pattern here, it can definitely make it look cleaner than this. If you use eSEES, the GUI, it's going to save them one at a time. Or you can write loops if you do this manually. Remember, though, that if you upload a file where you've done loops and then you save on top of it, you're losing all your loops. So you've got to be careful on how you manage your input files. But it's nice because it gives you the options. If you scroll down, once you're done with all the materials, you can then define all your sections. So it's interesting because in this example, I did for the sections here, these are fiber sections. So the fiber sections I don't have to worry about if I go into 2D or in 3D because they're automatically defined in both. But for example, now what I did was I just did some 2D hinges for the, for the beams and columns. But if I want, I can now go in and change this globally to concentrated hinge 3D. But you've got to remember that in 2D, you only have to define the Z moment. In 3D, you have to define the other, moment and other properties with torsion and everything else. But it's really nice and easy to be able to expand this. And this, for example, is something you could totally put into a loop because you're defining the components where behaviors are based on the material that we defined beforehand. So these are almost the same, they just have different references. Here you go down to the different element types here, but these aren't, I'm supposed to remove these because the program generates this itself, so these shouldn't even be here. I saved them at some point in between, and then they kind of just stayed. Then these are my different loads. So the default gravity is just something by default that's there, but then we define a load that we call pushover, a uniform sign. Again, these are things that are defined by default. You can even erase them if you don't use them. There it is. And then these are my model loads. I've defined the dead load and the live load and that earthquake one. And then, you know what? I think I do need the pushover though. So I just don't need a uniform sign because I didn't subject it to that. These are the different analysis models that we used. Again, you don't have to specify these. The program has built these for you. And here's our load combinations. So we've got gravity only, which is live load and dead load. So these are the two loads that we define, a pushover and an earthquake load. You can put this into a loop of defining many different ground motions, or you can copy this and change the direction and do more like that. Here's the model for our interior elevation. This is a fiber sections. And so you define the geometry, the columns, the beams, and for each beam, the gravity loads on that beam. If you look in the video, I did this afterwards for the hinges, but then the gravity loads, I actually define them as a bay range and a floor range, and then because I saved on top of it, the program itself spread them out nice and easy for all of them. And that's it. That's all there is to the input file for eSEES. What the program does, it creates an OpenSees file. And so here's OpenSees where the nodes, elements, boundary conditions, but this is all done by the program itself. Lots of really good bookkeeping. I try to make the OpenSees input file as well documented as possible so it looks clean and you can see what it is that I did. And then element loads and so on. And then these are all the little analysis loops and period and different computations that are needed. You don't have to write these, the program itself writes these for you. But of course, if you need to do something special, you can always use eSEES to start off, build this OpenSees input file, and then start working on this. You can't go back to eSEES because you lose a lot of metadata, but I think it's just also a good way to start building a model if you're doing something complicated. And same thing with the ground motion, everything is the same until you get down to the input and the fact that you're doing a time history analysis. Again, you can go and put this into loops itself, or you can work with this OpenSees input file yourself. So this is kind of nice, and that's what eSEES does. It makes OpenSees easy. Thank you. Bye-bye.